For thousands of years, humans have sought out how to increase their food supply. They have created large fields of crops filled with various foods to help sustain human life. The environment is not perfect. The soil in which we raise our crops can be infertile, and as plants use up nutrients in the soil, they must be replenished. To increase the fertility of the soil, we discovered that we could add manure to the crops to improve the soil's structure so that it can hold more water and nutrients. Plants need four main nutrients to maximize their growth: nitrogen, phosphate, potassium, and sulfur. In the 21st century, manure is seldomly used to provide these nutrients. Instead, farmers and agricultural businesses all across the world apply fertilizers to their crops to increase the rate of growth of their plants. The fertilizer we will be focusing on this video is anhydrous ammonia. However, the invention of this type of fertilizer derived from a much darker path than what you would think. In the early 20th century, German chemist Fritz Haber attempted to find a way to aid Germany in World War I. Realizing that ammonia is really useful in the creation of bombs, he began searching for a way to take the nitrogen and hydrogen from the air to create ammonia. Haber pumped nitrogen and hydrogen gas taken from the air in a steel chamber, increased the heat, and increased the pressure. This reaction yielded a large amount of ammonia. Little did he know that a discovery which would help kill millions of people would also end up saving billions of lives. Now, let's talk about the Haber process. If you look at the given equation, due to Le Chatelier's principle, if you decrease the heat and increase the pressure, equilibrium will shift towards the product side of the equation. Therefore, more ammonia is produced. In fact, 1 to 2% of the world's total energy use is dedicated solely to the production of ammonia. Plants need nitrogen to grow, and even though our atmosphere is 72% nitrogen, it is extremely stable, and plants cannot break the triple bond that holds nitrogen together in its diatomic state. Plants are only able to take up nitrate, which is what ammonia converts into once it is in the soil. Ammonia at room temperature exists as a gas. For storage and transport, it is pressurized in large steel containers which, when under pressure, will convert most of the ammonia into a liquid. Ammonia has a characteristic, sharp, and very pungent odor, which is caused by the fact that it is made of hydrogen and nitrogen, which both form very smelly compounds. Recall amines and amides. The Vesper shape of ammonia is trigonal pyramidal, with two lone pairs on top of the nitrogen. The molecules are held together by hydrogen bonds, and the dipoles only have a small electronegativity difference of 0.9 Paulings. It is due to this small difference in electronegativity that ammonia exists as a gas at room temperature, and has a lower melting point of minus 77.7 degrees Celsius, and a lower boiling point at minus 33 degrees Celsius. The polarity of the ammonia molecule allows it to easily dissolve into water. Anhydrous means without water. Household ammonia contains about 95% water, and anhydrous contains little to no water. 1 cubic foot of water can dissolve up to 1,300 cubic feet of ammonia vapor. It is ammonia's great ability to absorb water that makes it also very dangerous to handle. If ammonia comes into contact with a mucous membrane, it will rapidly react with the water, creating ammonium ions and hydroxide ions, due to the fact that ammonia is a weak base. These hydroxide ions can severely irritate mucous membranes, and this is why it is required to have a water tank mounted on all anhydrous tanks to flush out any ammonia that may come into contact with you. In order for ammonia to become available for plants to absorb, it must undergo a process called nitrification, where the ammonia must be oxidized by first being converted into nitrite and then nitrate, which is the form available to plants. The reaction is caused by bacteria in the soil and can be expressed as a redox reaction. NH3 plus O2 becomes NO2 minus plus 3H positive plus 2 electrons. NO2 negative plus H2O becomes NO3 minus plus 2H plus 2 electrons. On the flip side, an issue with all nitrogen fertilizers is a process called denitrification, where bacteria in the soil reduces the nitrate into gaseous ammonia, which is unavailable for plants to use. the denitrification reaction can be expressed as 2NO3- plus 10 electrons plus 12H plus becomes N2 plus 6H2O. The many benefits of nitrogen fertilizers have been seen around the world for decades and are crucial to feeding the growing population of the world. In fact, a third of the Earth's population is fed thanks to the Haber process, which allows humanity to access the nitrogen stored in our atmosphere to create ammonia. Without the use of nitrogen fertilizers, it is very likely that the expanding population of our planet would be faced with mass starvation. Mankind's abstinence from deforestation of important forests for farmlands is another crucial benefit of our advances in nitrogen fertilizer technologies. The Earth's wide range of forests are crucial in the removal of CO2 emissions from our atmosphere, and without them, we face a wide variety of climate change threats. As the human population continues to grow at an average of 80 million per year, it is extremely important that our food production also grows to continue to feed the populace. The best visible route for mankind at this point in time continues to be the nitrogen fertilizer at our current disposal, which we will continue to develop to gain the largest amount of growth rate gains as is safely possible. While nitrogen fertilizers have many benefits for society, there are also many risks and problems created by their creation and use. The production of nitrogen fertilizers requires an excessive production of ammonia using the Haber-Bosch process. This process requires extremely high amounts of energy and pressure, which in turn consumes large amounts of energy at a constant rate. The production of this ammonia alone requires 5% of the world's natural gas production, which is equivalent to 1 to 2% of the world's total annual energy consumption. This large energy consumption contributes to numerous different problems that stem from the world's energy crisis, such as global warming and air pollution. When added to soil, approximately 1 to 3% of the nitrogen is converted to NOx, or nitrogen oxide, while it is in the process of converting into the nitrate that will be used by the plants. This NOx is then released into the atmosphere as a gas, which will then bind with raindrops and becomes a well-known contributor to the problem known as acid rain. Acid rain has devastated numerous ecosystems in Canada, causing almost irreparable damage to the aquatic life of Canadian lakes and fisheries. In addition, the overuse of nitrogen fertilizer can cause great damage to ocean life. The extra nitrogen and oxygen molecules not used by plants and crops becomes a runoff which is slowly polluting oceans and creating vast dead zones. This occurs through the fertilization of algae by the fertilizers, which will then deplete the oxygen in the ocean and create zones of ocean floor where no aquatic animals or plants can live. Some of the major producers of ammonia-based nitrogen fertilizers in Canada include Yara Belle Plaine Incorporated in Belle Plaine, Saskatchewan, Koch Industries in Brandon, Manitoba, Agrium Incorporated in Carseland, Alberta, and CF Industries in Courtright, Ontario.